thank Kevin Porter for having invited me to make this presentation today to share with you my overview of the advanced composite manufacturing, recent advances, challenges, and opportunities, and also the opportunity to present some of the results of the work that we have been working at Concordia on the automotive composite manufacturing. So my outline to the presentation consists of 5 different items. First, I will talk about the focus of the presentation. Next, I will talk about the use of thermoset matrix composite in automotive composite manufacturing, and then thermoplastic composite, and then future outlook and conclusion. So first is the focus of the presentation. To define the focus, what I need to do is to define what it means by automotive composite manufacturing. In my opinion, any manufacturing process that utilize machines with some degree of automation can be qualified as the composite or automotive composite manufacturing. The reason why I need to do this because when I was organizing the previous symposia on automotive composite manufacturing, I need to make a decision to see which abstract should be accepted or not, because there are people that claim that they are doing automotive composite manufacturing that may not be. So with this definition here, I think that the field is very large. And for that here that I want to really qualify in terms of some of the aspects that I will not cover in this presentation. So the first item here is filament winding. I think filament winding definitely is an automotive composite manufacturing process. It is an additive manufacturing process as well, and actually some of the AFP ATL were based on filament winding. There has been a lot of literature and information on this technology. So I said I will not discuss this technology in detail in my presentation today. Another process that is also qualified is automotive composite manufacturing, that is pultrusion. And pultrusion can be used to really kind of manufacture many components with uniform cross-section effectively, economically. And again, this technology has been around for many years. There's a lot of information about it. Again, I will not include this in my presentation in detail today. Another process that also can be qualified as automotive composite manufacturing is thermostamping. So thermostamping is similar to compression molding, except that it is more, the temperature of the panel may not be that high. And as such here, then people use this technique to be able to make small components with complex geometries out of thermoplastic composite fairly well. But again, due to the lack of time, I will not discuss this topic in detail today. Another topic that is also of importance and qualified is automotive composite manufacturing. That is the case of the material handling, pick and place. Now, I think the presentation of Sue Patrick earlier today, she mentioned quite a bit of this technique. In the sense that this one here is some kind of robot with the actuators. And the actuators, at the end here, you have some kind of suction cup. And they use the suction cup here with the actuator to be able to place against some kind of prepreg or some kind of material, and then you can pick it up. And you can pick up these things here to transfer from one table to another one, such as the case from a layup table to some kind of a mold surface, for example. So this kind of thing will be useful to transfer prepreg, dry fibers, auxiliary materials, backing material, etc. So this is a very powerful technique in terms of trying to transfer the materials. And again, I don't have time to go over it in detail, but recently there is a review paper in 2018 that addressed this technology. So in case of for people that are interested, I think you can take a look at the review paper. So what is it that I will focus on? I will focus on 2 technologies. That is a case of ATL, automated tape layup, and automated tape placement or automated fiber placement, or AFP. Now, the reason why I want to focus on this is because these are new technologies and they have been used quite a lot in the aerospace industry to make many components for the airplanes. So along this line here, then I will talk for this technology, there will be 2 aspects of 2 kind of material that these 2 processes handle. One is thermoset matrix composite. Now, for the case of thermoset matrix composite, we have not done a lot of work at Concordia, so I may obtain information mainly from the literature in terms of this particular aspect. And also the case of thermoplastic composite, where we have done some amount of work. So I will talk more about our work on thermoplastic composite using AFB later on. So the idea for the factory of the aircraft in the future. I show you two pictures. One on the left, that shows the case of the conventional way of making aircraft component using composite. So mainly it's by hand layup with a lot of people around. And the other picture on the right-hand side, that is the case of the picture of the automotive application, where there's a lot of robots. So there certainly, we may think that, okay, in the future, probably the manufacturer of aircraft may look something like the case of the automobile. So maybe, we don't know yet. But at the present time, in terms of the way how the AFB and ATR are used, and they're mainly used for making large, simple structures. The objective of the automation for the of composite manufacturing is how to deposit materials at high speed with good accuracy and few defects. So three main items: high speed. I mean, you need to be able to deposit material with a large amount of material within a certain time, precision, and also few defects. So you can take a look here in the case of you have the this gantry is depositing these kind of laminate onto this kind of a mold. And you can see this laminate is huge. This you can compare against the size of a person and see how huge that is. Now the reason for that is because of the fact that in order to be able to deposit material at a high speed and so on, then you can mainly work on large parts and also limited geometry complexity. So for this, I find that in order to be able to do this, and I find the thermoset composite, they are more suitable for this kind of process than thermoplastic composite. And I think there were a few questions in the previous presentation about thermoplastic composite, that I feel that thermoset composite is more suitable. And I would mention about the reason for that a bit later on. So now we look into the case of use of automation for thermoset matrix composite. Now for the case of thermoset matrix composite, the main concern when we lay down the layers is for them to stick together. When you lay down a lot of prepregs for them to stick together. So for this here, the temperature that we need is not too high, so maybe between 40 degrees to 60 degrees centigrade. And the objective is mainly trying to make sure that is the tacky, that means stick together so that they can make it one single piece. So along this line here, I think that thermoset matrix composite have established a foothold to be accepted in the aerospace industry. And many major companies such as Boeing and Airbus have used automation as a way how to make many large structures. I'm sure everybody has seen these pictures in terms of making the fuselage, either for the Boeing 787 or Airbus 350. So what are the issues right now in terms of the improvement of the use of automation for thermoset matrix composite? So we're going to find here there are few aspects. These are the speed of deposition, efficiency of machine use, inspection, fiber steering, and dry fibers. So the speed of deposition and the effective machine use. First, I want to show you just a lap time machine. This is the lap time machine we have at Concordia. So I'll show you quickly just the kind of motion that is taking place. So this basically, that is a lap size machine, but that is a big difference between the case of a production machine. Now, I mentioned before, the production machine in the real aircraft manufacturing is very large. So when we work with the lap time machine, we may not see issues that people in the production area may see. And because in this case here, then the objective is trying to deposit things very quickly. And there are many items that people spend the time to study. And basically, they do some kind of a time motion, the time analysis of the machine, to see what aspect of the machine takes a certain amount of time. So here we have the one aspect, the loading the toe. I mean, if you have a machine that have 32 heads, you spend some time to load the toes on, so that takes some time for that to happen. The next one here is the different modes of material deposition. I mean, during the time that you deposit the material, it depends on whether you have a continuous course of the machine running that can go very high speed, they call it the mid-course payout. Or you have some kind of a location where you have to slow down, where you have to add or you have to cut the toes. Or you have a small piece with a gap. And another motion here called the off-back motion. That means when the machine had to go back from the beginning so that to lay down again, so they get off away from the surface of the part. So that's an off-back motion. Another activity of the machine called reliability recovery. So that means during the deposition process, there are many issues that is splicing the toe ends. That means you are at the end of a creel of the fiber that you have to connect the two ends together. So that means spend some time to splice them together. Or if the toes are broken or the toes are twisted or the toe may be sticking to the roller, then again, you have to spend some time to repair it. Then another activity that the machine has to spend is inspect and review. I mean, after you deposit the layer, then people have to make sure that it's okay, so they have to inspection. Now, it depends on the inspection, whether a manual or automatic. If it's manual, it takes a lot of time. I will mention about that later on. And then after you found the defect, you have to decide what to do with the defect, the treatment of the defect. If the defect is not that severe, you may neglect it. If it's critical, you have to repair it, or maybe it's too bad, you may have to reject. And another item here called the tool move and weight. So here there was a paper in 2019 from the people in Electro Impact Company. And in that one, they make a statement that I find to be kind of provocative. It says AFV machines in aerospace manufacturing spend much of their existence doing nothing. So that is a very provocative statement. Now, these machines are very expensive, tens of millions of dollars. That would be a crime to say that the machines sit there and doing nothing. So what is the reason why they say that? Now, the reason they say that is because they analyze the different kind of time, motion that I mentioned to you in the previous slide. And they find that in the previous way, the layup time, that means the real production time, the time when the machine lay down the material is only count for 19% of the total time when the machine goes into a production cell. So what happened to the other time? The other time here, the inspect and review, that's 42% of the time. Now, inspect and review, that means what they did before is that they have to do that manually. That means they have to get an operator to go and look at every part. So it becomes very fast to deposit, but it takes a long time to inspect. So that is not very good. Then you have also recovery, reliability recovery 14% of the time. Tool move and weight, 517, and the break over at 8%. So people have improved it to the current technology by 2019. Is the layup time increase of 42%. Inspect and review go down to 28%, and the other three aspects remain the same. And then hopefully in the future, they want to improve the layup time to 76%, and the other time remains similarly. So this slide here, again from the Electro Impact in 2017, they give some of the speed and the position of the head. So this one here, this is the head from Electro Impact. And in this case here, it has 20 toes, 1.5 inch wide. So each time it can lay down 30 inch wide of the materials. And here they lay down on a large surface with the low contours, with the four heads. So the speed of the maximum speed that can be laid down is 4,000 inches per minute, which is equivalent to 6 kilometers per hour. And that way corresponds to more than 3,000 pounds per hour of material deposited. So that is a fast speed. If you have to add and cut, it go down to 1,200 inches per minute. And the minimum gap, we have 600. Off-back motion, 6,000. So out of the average, out of all these different time here, the average amount of material deposit is about 900 pounds per hour. So that shows the kind of the speed of material deposition. The next aspect here, that is inspection. That means the case that how much time do you have to spend to inspect. So this case here in the past, a lot of AFV, they are done by manual inspection. And that consume a large amount of time, and sometimes you may miss the defects. And the time can be more than 25% of the total time and may escape detection. So over the past few years, there have been quite a bit of activities addressing this issue, including universities and companies to look into this aspect. So in 2016, there was a paper presented from people in Germany, and they developed a system called tomographic system. Tomographic system, that means in this case here, they get an infrared camera, and they observe the surface of the player that has been just deposited. And by doing this, then they can detect the toe location, gap, lapse, and foreign bodies. In 2019, there was a publication from the National Research Council of Canada. They worked together with PHI's machining system, and they developed a system called optical coherent tomography. And this is similar to ultrasound imaging, where they use some kind of a light to be able to detect over the surface. And by making a scan over the surface of the laminate here, they are able to see some kind of deviation whenever you have something like a toe plies or a toe wrinkle. And from the industrial side, again, from the electro impact people publication in 2018, they have developed a system where they use a laser. You have the profilometer, they have the projector laser line on the surface of the substrate. And for this here, they were able to detect more than 1,000 toe ends in a few minutes. And they identify 92% of the toe end in the start apply. So this system here, they were able to detect the presence of the defect effectively within a short time. Now, for this kind of inspection system, there is a need for software programs. There's a lot of information that is generated. You need to have software program to be able to handle the data. And the data can approach more than 1 terabyte per part, per complex part. So this one here, the huge amount of data that had to be processed. And however, it can reduce the inspection time, reduce human error. And besides that, they can also have some kind of statistical process control to eliminate unnecessary fixes. I mean, there may be some kind of defect that may not be critical, and you may neglect it, or maybe there are something that more severe, you have to work on it. However, this machine here is not cheap. It costs more than $1 million. And besides that, also the manufacturer need to make decisions about what to do with the inspection data. So that means after you have seen the data, then you have to decide what to do with that. If the defect is not severe, you say, okay, I can live with that, I can move on. If the defect is significant, you have to repair it. And if that is too critical, you may have to reject the part. So in last year, there was a publication from people in the University of South Carolina, and they identified 14 different kind of defects, 14 different kind of defects inside the laminate made using AFB. So they lap, overlap, pucker, wrinkle, ridging, boundary coverage, angle deviation, fold, twist, wandering toe, loose toe, missing toe, splice, position error, and foreign object. So identify 14 different kind of defects. And they also classify the defects based on 5 perspectives. So what are the 5 perspectives? The first is anticipation. Anticipation, that means the way that you can predict the defect based on the computer-generated fiber path. Because in automation, you have some kind of computer to generate the fiber path, and you know where the fiber is. So depending on the fiber path and the relative geometry of the part, you can predict whether there will be some defect at a certain location or not. The second perspective is existence. Existence, that means that whether your inspection system can detect it. You use some system whether you can detect the defect. The third one is significance. That means that what is the effect of the presence of the defect on the performance of the part, whether that's critical or not. The fourth one is progression, whether the defect will grow during the process. And the fifth one is deposition, what to do with the defect, whether the defect is critical or not critical, and you have to make a decision on that. So they also made a survey of the work that have been done on the effect of the defect on the performance. So there have been quite a large number of papers published on the effect of the defect on the performance. And from this survey, they found that for the case of quasi-static loading in unnotched unidirectional laminates, that the effect is not significant. The effect on the performance is probably less than 10%. However, the effect is more severe in fatigue loading, where the effect of the defect can be up to about 30%. They also mentioned that due to the fact that you have a large number of defects, and also due to the fact you have different geometry configuration, large number of layers, so the work that has been done up to now is only looked into some very limited configurations, and a lot more work needs to be done before we can really understand the effect of the defects to have a grasp of what happens. So the next aspect here concerning the AFB is the fiber steering. So certainly one of the nice feature about using the automotive placement is that they can steer the fiber. You can see that you have this here, and also there was work done at Bristol some time ago about the toe shearing, which is a similar aspect to be able to match the fiber that is curvilinear. However, there is a minimum limit radius that you can steer, because if you can steer lower than the minimum radius, then you have defect, such as the case of you have the buckling, wrinkle, buckling, and so on. And so in order to be able to really kind of improve this, that you need to have a precise and focus the heat and the good compaction pressure to be able to control this aspect. And people found that the laser heating is a better way of heating than the case of, because it has more focus and good control. So there are many factors affecting the steering radius. These are the toe width, toe thickness, resin type, resin tackiness, fiber type, fiber format, substrate contour complexity, substrate quality, arc length, and tolerance parameters. Now, from the publication from a few companies, electro impact corrogers and Ingersoll machines, they found these are the minimum radius that you can tow, that you can steer. Say for 1/4 of an inch tow, radius is 19.5 inch, 1/4 inch tow between 11 inch to 59 inch, 1/2 an inch tow, 6 inch. However, there was a statement from publication from this company that I find interesting. It says here, such steering sees limited use, given the fact that composite aerostructures operate in a certification environment that favor traditional quasi-isotropic life schedules. So what this says is that at the present time, maybe the industry are not using it yet. However, I think the work done, mainly academic, but I think will be useful in maybe the future and also from other applications. Now, the last thing I will talk about the case of the thermoset composite is dry fibers. Now, the reason I put the dry fiber within thermoset composite is because when we do the automation to make the dry fiber, we make only the preform. And after you have the preform, you need to infuse resin into the preform to make the composite. And normally people use thermoset matrix as a way to, as a resin to infuse into the dry fibers. The case of dry fibers, normally they have to use some kind of a thermoplastic binder. And during the process, the thermoplastic binder need to be melted so that you can free the fiber. As such, you need to have a good amount of heat. The temperature is between 160 to 200 degrees centigrade to be able to process it. So the advantages and disadvantages of the dry fiber. So the dry fiber, because of the fact you don't have resin, so that means the downtime, event and repair times are less for the AFV processing. They say that people feel that they can increase from 15 to 30%, increase the machine utilization. And also the fiber have better tension control, and such a speed can be larger. And people usually use laser focus the heating on the active dose. However, there is disadvantages. I mean, the development of fuzz. Fuzz, I mean, you have the fuzzing of the fibers because they are dry fibers. In this case, they can result in some kind of foreign object debris creation on the laminate. It also requires a higher temperature heating and fiber tension control. And because of the fact that you use higher temperature heating, you have to use a strong laser. And you use a strong laser, then you have to provide safety measure because it can be dangerous in case it hits somebody. And also the laminate have a lower tucking, and this makes the part more fragile and produce challenges on thicker layer. So there was a publication in 2019. They were making two kinds of laminates. One is by manual, I mean by hand layup, and then they infuse resin into it. Another way use a dry fiber, and that they also infuse resin. And they were comparing the laminate made with two different kind of method. Manual means hand layup, and ADFVM is the automated dry fiber placement. So when they make the preform, they found that the preform made by AFV is thinner, 1121 to 1156. It weighs less than the case of the hand layup, and also, but in this case, when you make the laminate, then the laminate become thicker. The reason for that is because during the laminate fabrication, people apply pressure, and the pressure has more effect on the the preform than the case of the AFP. The fiber volume fraction in the case of AFP is larger, less void, and also you use less resin. So these are all advantages of the automated fiber placement for dry preform, except for the filling time. When you are filling the resin into the composite, then it takes longer, more than 2 times the time required in order to fill. So next here, I talked about the use of AFB to make thermoplastic composite. So thermoplastic composite is it depends on the kind of resin because of the fact that you have high viscosity. And so that means you need to really heat it up to high temperature in order to reduce viscosity. And so depending on the kind of matrix that you have, whether you have the PEI, PBS, or you have PIC, then the process temperature can vary between 275 to 400 degrees centigrade. So thermoplastic composite certainly has more issues than the case of thermoset. Usually the objective in manufacturing of thermoplastic composite using AFVR structure have minimum amount of void. have a good degree of crystallinity for the resin, no deconsolidation, no distortion, good rate of production, and good surface finish. And again, I mentioned there are many issues. The issue, the first one here is that we have, let's see, heating. The heat sources. Now, the heat source for the case of thermoplastic composite have to be stronger than the case of thermoset. That's because you have to melt the resin because of the high viscosity. So there are 5 different kinds of heat sources for thermoplastic composite. First, hot gas torch. So that has been around for some time. They use nitrogen as a way to heat. Direct open flame torch. Third is laser, which is, I think, more people use these laser these days. And recently, over the last few years, they have the heat lamp. And infrared has been around, but it's not as strong compared to the other 4 different kinds of heat sources. So in more detail, we have the direct hot gas torch or direct flame. So here we have nitrogen gas is heated by electric heater located before the tip of the nozzle. And the nitrogen gas, nitrogen flow can be adjusted. However, the disadvantage of this is that the hot gas stream cannot be pointed in multiple directions efficiently. And also there is a heat loss to the environment. Direct flame is similar to the hot gas torch, except they use propane gas and oxygen. And also the ratio can be adjusted, but it has similar kind of disadvantage like the hot gas torch, is that the flame cannot be pointed in multiple directions efficiently, and there is a heat loss to the environment. Laser, quite a few machines these days use laser. The power of the laser can vary anywhere between 3 kilowatt to 5 kilowatt diode laser. The wavelength is about 1,000 nanometer. The speed can be fast, from 8 meter per minute to 12 meter per minute. And one of the advantages of the laser is that they can use a soft roller. That is a case of made of silicone. And the fact that you use a soft roller like a silicone, it allows more larger area of contact between the layer of the composite. And that way you probably tend to have a good interlaminar shear strength. However, the disadvantage of the laser is safety consideration because of the fact that the heat is strong and you need to make sure that it doesn't hit the operator during the process. And over the last few years, there come the heat lamp, the HUM3. It uses high energy flashes via xenon lamp with heat the material through radiation. The 3-parameter voltage, frequency, and pulse duration. So the advantage of the heat lamp is that they can direct the heat in different locations, 25% toward the incoming tape, 35% to the nip point, and 50% directly at the substrate. The disadvantage is that it's fairly new, so that we need to kind of study and learn more about it. Now, one of the the kind of issue with the thermoplastic composite is interlaminar shear strength. What I find is that the interlaminar shear strength of laminate made by thermoplastic composite is not as high compared to the cut of the autoclave. So in a publication in 2019, there was a comparison between the interlaminar shear strength of laminate made by different kind of AFB using different kind of composite, and the value is about 50, something like about around 50 MPa, and that is compared to about 80 MPa. So that's roughly about 60% that of the autoclave. Now there are many reasons why the interlaminar shear strength of the thermoplastic composite made by AFB is not as high compared to autoclave. So what I find that there are basically 2 reasons. One is the bond formation, and the second is the consolidation out of the nip point. Now bond formation, in the sense that when you take a look into the process of the AFB, for example, you have the incoming tape here, and you have the substrate, the one that is deposited beforehand. And these two here have to come together and they have to bond together. Now, during this process here, you can break it down into many steps. The first step is that the surface asperities have to be flattened. So that means between these two surfaces, there may be some kind of a roughness, and these roughness have to be flattened, okay, because they get melted and flattened. Then the two surfaces have to get into intimate contact. They touch each other. Then the intimate contact has to be long enough. So that way, then the molecules of the thermoplastic can diffuse, can wrap that across the interface to make the bond. Now, also there is some kind of dynamic shear effect that may help to reduce the viscosity to do that as well. Now, there was some estimate in terms of the time required for the bond, the reptation to take place across. And this gives an equation as a function of the viscosity. The Etna has a viscosity in MPa. Now, if the viscosity obtained is around 1 kilopascal second, then the time required for the contact here has to be about 22.9 microseconds for it to happen. Now, on the other side of the picture, if you take a look into the parameter of the process. So the time that this is in contact is equal to the length, the contact length here divided by the velocity of motion. So this is by this equation. T equal to E. E is the length of the contact divided by V, which is the velocity of motion. If we take the speed of deposition is 4 inches per second, and E equal to say the 1/4 inch for the case of a soft roller, that the time is 62.5 microseconds. If the length here is only 1/8 of an inch, that the time is only 31.3 microseconds, which is kind of just barely enough to do this, except that this time here is only for the case of the reptation. It doesn't take into account the time required for flattening the surface apparatus and also for intimate contact. So that means in this case here that the time of contact is just barely enough or just on the borderline to be able to make a good bond. Now the second reason for this is we could talk about deconsolidation after the nip point. Here you have the roller that is pressing the layer down. Now afterward the roller moves forward and you have the region behind the nip point, that is the region between B and C. Now it depends with the temperature of the piece in this region. If the temperature here is more than the glass transition temperature of the resin, then what happens due to the springiness of the fibers, then it tends to deconsolidate. And when it deconsolidates, certainly it affects the interlaminar shear strength. Now, another issue with the case of thermoplastic metric composite is the distortion of structures with the free edges. Now, we identified two kinds of structure. One is structure without free edge, such as the case of a cylinder like this. For this cylinder without free edge, it's no problem. We were able to make them very well, no issues. However, for the structure with the free edges, that means that you have something like a flat plate, or the case where you have a curved panel where the fiber is cut. Then what we find is that right after the process, you have the distortion, even for the case of a unidirectional layer, when you make a unidirectional layer, okay? Now, the reason for this is because of the thermal gradient, because of the fact that the temperature varies throughout the space in X, Y, Z direction, in all directions. And this developed during the process. So that means right after you make, you also have this kind of situation. Now, one example of thermal gradient is that we take a look into, we find that also the laminates tend to bend. This one here shows a section of the thermoplastic composite along the width. So the distance from left to right here is about 1/4 of an inch, so the width. What we find here is that during the process, the width becomes longer. The width becomes longer and the thickness becomes thinner, which is expected. But what else that is observed is that we find that also this tend to bend like this. So this is schematic representation of the width of the laminate. So you take a look into the midpoint A on the left and the midpoint B on the right. You connect them with a line. So if there is no bending, then the point C and D should be the same. But if there is a gap here, there is bending. So the picture below shows you this one laminate. You can see that the line BC is here, AB is here. That's the yellow line here. And also this is along the line CD, and there's a gap. The same thing for the laminate below. You have the line AB here, and you have the line CD here. And it shows that you have a gap. So this one here, the reason for this bending is because of the thermal gradient that is developed. So now we want to show you some of the work we have done on thermoplastic composite at Concordia University. So over the past few years, we've been working with two major companies in Montreal, Bell Flight, and also Bombardier Aerospace. For the Bell Flight, we work on the development of a thermoplastic composite to use as a crosspiece for the support the helicopter as the landing gear. And the other one here for Bombardier, we develop a nacelle lip for laminar flow for the engine. So for the case of the piece, the cross piece for the landing gear, now right now it's made of aluminum, and the people that want to replace aluminum, there are many reasons for this. Okay, now the requirement for this is that it had to be stiff and strong, but also the challenge is how to absorb a large amount of energy on failure. Now we know composite are stiff and strong, that's fine, but the composite usually tend to be brittle. So how do you make sure that it can exhibit a large amount of energy before failure? So here we use thermoplastic composite because it tends to be better than thermoset in terms of the kind of energy absorption. Well, also, we have to design spatial layup in such a way that you can really have a large amount of energy absorption. So here, this one here shows you just a video about the way how we program the machine to be able to get the layup along the different kind of orientation to do this. And in this case here, then we have made a straight tube. We have also made curved tube, and also we have a setup that can do the bending. You know, can have the 2-point bending or 3-point bending, either on a straight tube or on a curved tube. Now, the work on the nacelle lip for the laminar flow for Bombardier and DMARC. So apart from the fact that we need to be able to machine to really kind of manufacture to the shape, but also the other aspect, they had to have good surface finish. Now, the reason for this is because of the fact that this had to allow air flow, and they want to have minimum resistance to air when it flows through, so they had to have good surface finish. So this case here, that means we have made the pieces here, and you can see that the way we address the kind of finish is by using a technique called repass. Repass, I mean that when you finish it, you only you can run the machine over the surface without any deposition. And the other aspect you have to address is distortion, and we have to use annealing technique to address distortion. In terms of repass means passing the torque and roller without material deposition. So we show you the measure of roughness, RA. If you make the thing without repass, the roughness is about 40 micron. One repass is reduced down to 5, and so on. Compared to autoclave is about 1. Now, along the fiber direction, the roughness before repass is 20. After 1 repass is 4, 2 repass 3, and autoclave. And also this one here shows you the microstructure. What we found is that the repass can also help to reduce the void content as well. So future outlook in the sense that what we go from here, you know, there are people that have certain opinion. One is that they feel about collaborative fiber placement. That when you use more than one robot to make a piece, okay? Now, there was a publication from Composite World in 2019. They mentioned about the system called GROFI from the German Aerospace Center. And in this case here, then they were depositing material onto a vertical mantle. So in this case, the robot is placing material on the vertical mantle. And you can use more than one robot to do that. And normally they have the cell of 8 robots. And they are 4 and 4. So 4 robots are working on it, that are 4 robots in reserve. And that way they have some kind of a track to be able to move them in and out. So the kind of critical issues here is programming. They have to make sure the program is good so that they avoid collision between the robot, and also to make sure that each one of them does a portion of the job. Now, also the other thing that we feel about the future is that limitation application of ATR and AFB. Now, certainly ATR and AFB are very good in making large components. However, they are small parts, such as ribs, brackets. They may not be efficiently used ATR and AFB. And also has a complex feature, such as double curvature, tight corner, and steel ramps are challenging. And also the capital cost is very high. These machines cost $10 million, and many small and medium companies may not be able to enter into the technology. So we feel that right now, they may be something that may expand the use of automotive composite manufacturing is either making additive manufacturing or smaller AFB. So these are the other ends of the picture. The case of 3D printing with continuous fibers, you have the people feed in the resin together with the fiber, and that way right now the Mark Force company has 2 models, Mark II and X7. It can handle carbon fiber, natural fiber, and glass fiber. So right now we have the 2 spectrum. You have the large machines to be able to handle aircraft manufacturing, and you have the small piece made by either 3D or 4D printing, and hopefully in the future, maybe we can use these technology to make some kind of commercial products. And in terms of the small AFB machine in 2018, there's a company in Finland called Espoo. They developed a small AFB machine. The weight is 16.5 kilograms. It can sit on top of a desk, It can handle carbon, natural, and glass fiber, and it can do different kind of toes, 1/4, 1/2, and 1 inch. So my conclusion is that for thermoset matrix composite, they have been successfully used in making aircraft structures. Improvement can be made on speed, or deposition, automated inspection, reduction in medium radii for fiber steering, and understanding of the performance structure containing defects such as lap and gaps. For thermoplastic composite, we need to have improvement for the heat sink sources, and we need to address low internal shear strength distortion with structure with 3 edges. And future outlook, in terms of trying to go to commercial products, here will be smaller FE machines or 3D printer with continuous fibers. I would like to acknowledge the financial support from the Natural Sciences and Engineering Research Council of Canada, Flight, Bombardier, and DEMA, and also many of my associate and student and colleague, Daniel Roska, Xiao Kai, Fajat Chatmeri, Hang Wang, Juan Wendick, Jeffrey Simpson, Ashraf Fatih, and many students. I thank you very much for your attention.